Thank you very much. Thank you. Good morning, everyone. Thank you, first of all, to the organizer, Radu and Yura. It's a real pleasure to be back in Vienna. I love this place. I love the people. I love the food. So that's really, and organizing this wonderful seminar after this COVID period. So that's really good. Okay, so I'm going to tell you about non-smooth non-convex minimax. And this is a joint work with my, he just finished his PhD, Eyal Cohen. Went to do some money in the industry. People in the academic world. And so today I'm going to report on part of, essentially it was part of his thesis on this unified convergence analysis. So basically this is a modest attempt to tackle a non-convex minimax problem, and I'm going to explain to you what was known when we started this research, which was about 3 years ago, I guess. And maybe things have improved since then, but you will understand very soon where I'm heading to. Okay, so first of all, let me refresh your memory. Okay, so we are dealing with a min-max problem of a bivariate functional KUV. We'll adopt this notation, which is very convenient. You will understand very soon why. That's not important for the moment. I will be more precise in the next 2 slides. So, of course, we are all familiar with the convex concave case. The research goes back to von Neumann. Thousands of papers have been written on that, and there are still papers on the subject of convex concaves. There are still things that can be improved there. I'm not going to discuss this. So that's where essentially all the data are assumed to be convex. And of course, the coupling term is convex in U and concave in U. And as we know, there's some standard constant qualification. When we solve the min-max problem, we are searching a saddle point which satisfies this inequality. And that's more or less the story of the convex. So here we are going to try to do something which is beyond the convex concave setting. Okay, so we are back to the problem. So the motivation essentially came from machine learning and artificial intelligence problem. As you can guess, this has become a very trendy subject. And I'm not going to discuss all this. Actually, there is a very nice review paper already from the 20s from Razavian and his colleagues who give an overall perspective on what's going on non-convex min-max problem. Okay, so and at the time, at least that we started our research, and again, I'm not going to go through all the literature. The literature was already wide on that subject, and it was focusing on weakly convex, weakly concave problems. Now, just a reminder. Weak convexity is essentially saying that you take a function and you add a small positive term in general, then you expect that quadratic terms, and you expect that the resulting function will be a convex function. Okay, and so in these works, essentially most of the times the F and G were assumed to be convex, and in fact, many of these works that we have encountered in the literature were dealing with this problem, meaning that F and G was chosen to be the indicator of closed convex sets, okay? And the coupling function was assumed to be continuously weakly convex concave. And perhaps the most thing which was strange, and actually maybe the talk of Russell is supporting this, that we're a bit surprised to see that all the people are dealing with rate of convergence and complexity results, but no convergence results whatsoever. I will mention one singular point which was brought to our attention by a referee, but that was a result which was really completely impossible to use, completely irrelevant. So we ask ourselves, can we do something different? Okay, maybe we can get complexity result, but maybe we can get convergence result, and so that's what was the starting point of this research. And of course, we were a bit bothered by the assumption which were here. So we start to look at something different. You can relax. I mean, we are not claiming that we have solved everything. There is a lot left to do. So this is just a modest attempt to attack a specific situation, which was also motivated by modeling, and there are enough problems that can be modeled that way. So I will discuss that in a moment. Okay, so let me just show you the approach. Okay, the approach that we are going to look at. So as we know, as I mentioned before, in the convex concave case, a saddle point subject constant qualification is guaranteed. But when we quit the convex concave settings, then we don't know what we don't even have existence, and it's not possible to maybe even to compute. So there are many ways of looking at the situation. We choose, I think, the simplest one. And we are going to focus on stationary point, which satisfy first order condition. So first of all, if we denote the max part of this problem, okay, this is constant with respect to u, the function f. So we denote this function by phi u, and we define it as a maximum. And then essentially, when we look at the Minimax problem, we can always think about minimizing a function, which is given by the sum of two functions, f and phi. And so we want to focus on finding a critical point of this sum, okay? So of course here, this function is a sum of a non-convex, non-smooth function. We don't also know anything about it at the moment. And so we are talking about a critical point. When I say critical point, I'm talking about the limiting subdifferential. And the nice thing that we know is that if we can warrant that the function phi is continuously differentiable, then we have these differential rules, which is also working for the limiting subdifferential. So this, the limiting subdifferential of theta is the sum of the subdifferential of limiting subdifferential of f plus the gradient of the function. Okay, so that will be the approach that we'll be following here. Okay, so as I said, we are going to make some assumption, no free lunch. But let me just show you what people have been reaching, was what I was talking about rate of convergence before. Okay, so usually people are assuming that this KUV is weakly convex concave and that the domain of G is compact. Is also something which is seems to be crucial in their analysis. And so the advantage of it is that in that case, you can show that the resulting max here function is also weakly convex. And then people have been focusing on the complexity of obtaining a nearly epsilon approximate solution. And why is that? Because there are two very nice properties, which I think was discovered by Davis and his colleagues on weakly convex functions, that if you look at the Moore envelope of a weakly convex function, then you get a smooth function. And then, of course, you can look at the approximate stationary point of this smooth function, okay? And this gives you exactly this nearly epsilon approximate stationary solution of theta. So you want to find a point where the distance from 0 to the subdifferential of u is less than epsilon, where this is in the neighborhood of this u hat, okay? So this was the kind of approach that had been chosen in many papers, have been written also in the all conferences type of paper and so on, and looking at the complexity of the problem when working under this assumption. Okay. Now, if the function is not weakly convex, then theta is not weakly convex and everything collapses. You cannot do that. I mean, you cannot use all these beautiful tools. And so that was another additional motivation for us to look at something different. Okay. So what we are going to, I'm going to show you the basic model and the algorithm. There is nothing new on neither maybe on the model nor on the algorithm. What is new is the convergence analysis, which I think is extremely elegant and powerful. Okay, so this is a class of problems that we are going to study. We are going to make an assumption here, where in the second variable, this is going to be strongly concave. Okay, you can say, well, this is a strong assumption, strongly concave. Yeah, it is. I mean, but that's life. You have to pay a price when you want to get results. And besides, think about, for example, composite optimization, nonlinear composite optimization that can be written that way. There are many interesting problems that can fit that. I'm not going to enter to the class of problems that you can solve, but there are some interesting problems that you can solve here. So here we are assuming on the other hand that the function f is just proper Laurent semi-continuous. So this is non-convex. It can also deal with the extended value allow you to handle also non-convex constraints. So this is an advantage. You can handle, for example, L0 type function, L0 type constraints, things that cannot be handled with all the models that we have been discussing before under the assumption of the previous weakly convex concave. Okay, now we are assuming also smoothness is the in the coupling variable, which is assumed to be concave. So this is actually all these inequality are just to separate the constant, because sometimes you can get better constant when you compute the step size of the algorithm. Of course, you can think about the general global. Now, how about the rest? Okay, so G is convex, so that this becomes concave. And then we assume that this object, the G minus C, is sigma strongly convex. Now, we could, of course, assume that only G is strongly convex. Okay, that would do. This is the reason that we choose to put them all together. You can also do the decomposition as you wish. It's just more convenient from the standpoint, again, of computing constant and so on in this business. So this is a setting. So again, we are dealing with non-convex, non-smooth bats in the mean variable, but strongly concave in the max variable. Sigma depends. No, does not. This is a global, completely global. Yeah. Okay. All right. So, as I said, whatever we are suggesting here is, of course, this is just an extension of the classical gradient descent algorithm for solving min-max problem. Okay. So here, since we are dealing with f and g, we are going to do a proximal gradient. Now, I want to just to emphasize that here, we decided to go and analyze two algorithms. Okay, there is what is called the parallel version. So the parallel version is when iota is equal to 0, meaning you are computing U and V simultaneously, or simultaneous version, as you like to call it. Okay, or that was just to write another paper. Since I knew that Eyal is not going to the academic world, he didn't know enough publication, and I always try to minimize when I think about the subject to minimize the writing of papers at my age. That's logical, I guess. But for young people, it's not a good idea. But anyway, so this is handling essentially with this parameter. This is actually, it's beyond that. It just turns out to be a very neat analysis of two completely different algorithms. Okay, so this just index is controlling. Okay, so when you take one here, okay, then of course you see that's k plus 1, so you are doing the alternating version. So you use first of all the maximization in V, and then you compute the U. Okay, so this of course prox operation, the usual prox for an arbitrary function, which of course may not be unique or exist. We have all the standard condition for that in the non-convex setting. Okay, so let me just so this is if you prefer, this is just an explicit writing of the thing, and that's why this is called the proximal gradient. As you can see, I'm going to the letter. Basically, we can show that this algorithm is emerging from doing an approximate proximal method on the original reformulation of the min-max problem as a mean problem. I'm skipping all these details. Besides, there are many experts here that I'm assuming that they should know that, but anyway, that's also a nice part. This is helpful to think about generalization. I will mention that at the end. Okay, so we have here a single loop. That's why we do this approximation. So this is either parallel or alternating. This constant, we'll see from the analysis, will depend on the Lipschitz constant, and we'll see how. And as you can see, of course, we will be able to handle both cases at once, either the parallel or the simultaneous. Okay. And actually, there is also a nice thing which is common, I think, in the literature, in the old literature, even the gradient descent ascent, that we know that when we do parallel methods, they are supposed to be worse than alternating. Alternating also are supposed to be much more difficult to analyze than parallel methods. Well, it turns out we didn't find any any difference. So that's why we dealt with both. But here you can see, for example, that we can see that there is a trade-off, and I will show you the formula just for the sake of fun at the end, that indeed we can realize here that we get a larger step size when we do alternating prox versus the parallel one. So this is just confirming what people have been experiencing in numerical settings. Okay. All right. So the problem was, how do we handle convergence? When I said convergence, we are going to deal with both the complexity, but that was less important for us. The more important thing was just to reach some kind of convergence result for the setting. Okay. So here we are experiencing a big issue. It's 25, not 30? No? 5 minutes questions? Okay. All right. So, tough chair. You know that I'm coming from the Middle East. We are used to bargain. What? So anyway, we'll see. I don't have much actually. I want just to send you the messages. So the so-called gradient-like descent sequence, if you are not familiar with this, which comes from the joint work in the Palm stuff, cannot be applied here. And that's the reason is that we have a min-max structure and we cannot even construct a Lyapunov function. Actually, I would put a parenthesis here. That was a single paper that we didn't discover, a referee discovered for us, mentioning that somebody tried to prove convergence. Indeed, they proved convergence by trying to force and apply this. But forcing to apply this, they put 3 conditions which are completely unverifiable, impossible to verify, impossible even to define. I would say that up to this level. So to just impose to us it was not surprising, because that's why we tackle the difficulty. We overcome this gradient-like business by defining what we call the perturbed gradient-like methodology. And I'm going to show you. And the purpose was, of course, to get global convergence of both the parallel and the simultaneous version in a unified manner. And actually, this is interesting. I think that this is very generic, again, and it can be used in many other contexts. I'm pretty sure that people will find application of this. Okay, so what is the perturbed version of the sequence? So we have a functional here, extended value, per hour. We have a sequence of point xk and a scalar non-negative sequence, where sequence in the domain of psi and the non-negative sequence. And we say that this pair is a perturbed gradient-like descent if it satisfies the 3 conditions. The first condition is that it's a kind of perturbation of the sufficient decrease in a very peculiar way. As you can see, there is a difference. This is the term which appears here. There is also the second term, which is a perturbed self-gradient lower bound, which is given here. And the third condition is standard sort of continuity condition with the lim sup, which is upper bound with this. So obviously now, since people, if you are not familiar with the classical gradient-like descent sequences, if you plug OK equals 0 identically, then you get exactly this. This is 0, this is 0, this is 0, so this is exactly sufficient descent. This is a gradient lower bound. This becomes 0, and this doesn't change. Okay? So, of course, when we do that, okay, we define a very abstract concept here. And the main thrust will be eventually to identify what will be this perturbation and what we can do with it. And the point that I want to mention that all this does not enter in the algorithm. I mean, this is just to prove things, but the algorithm is free of all these parameters that are appearing here. Okay, so we prove this very general key lemma and the iteration complexity. We built a functional LK, which is psi of xk. This is an arbitrary function. It has nothing to do with the min-max issue. This is just a general methodology. We added these quadratic terms. And we can prove that for this, the C1 is satisfied. And we can also prove this to this type of rate of convergence on the consecutive sequence. We can prove that this perturb parameter is going to 0, that this is also this 2 consecutive sequences going to 0. And thanks to this, if we assume that C2 is holding, then we can get this kind of complexity result, which is classical in the sense that we are dealing with non-smooth, non-convex stars, so we are getting something of the square root of n here. So this is a very generic result. So the idea, of course, since I have not much time, so I will skip. So having that, we can prove subsequence convergence, okay, which is given here, okay? And we can also get global convergence, assuming that psi is semi-algebraic, and of course, it's, for example, we can use the standard KL Krudical-Rezevich theory to achieve this. So all this framework is very general, and I guess it can be used in other contexts. So what do we do with it? Well, so we want to prove a result for the two versions here. So we focus on the U step. Remember that the U step is given by this, and the iota is controlling both algorithms. We can find two estimates here. We can actually I didn't want to bother you with the formula. We can write explicitly all these. All these are not needed in order to implement the algorithm, but we can compute everything. Now, when you look at these two inequalities, you can see that this is nice, okay, but this is not. Because, I mean, this is just destroying the, for example, the sufficient descent. The same for the subgradient descent. We have this garbage here, which is apparent. So basically, the entire analysis, okay, for both cases, was to try to prove C1 and C2 in the general model, okay? And in order to do that, we had to find proper estimation for the norm of this and the norm square, to identify, more importantly, what the sequence of parameter is, and of course to set the proximal parameter alpha, which is here crucial in the to do the computational step. Okay, just to give you an idea, I mean, these are just very neat formula because they are all closed. Everything is well defined. You have all the parameters here which are defined in terms of the Lipschitz constant. You have your iota, which define which class of algorithm. Again, I reiterate this is only required for the analysis. You can see that this term is vanishing when we are in the parallel setting, and you can see also, okay, so the parameter, the computation is given here, and if you plug the numbers, these are just pure arithmetic, so there's nothing to do here. You can see that you have a smaller U step size when you are in the parallel setting. This is also a bonus kind of information, which confirms what people have been doing in a numerical experiment. Okay, so I'm good. This is what we can prove. We can exactly find the three conditions for the PGDA. The PGDA, I recall, we can identify all the objects, and then we can get also the iteration complexity, which actually fits, but differently from others so far. We get true complexity result, not nearly approximate, okay? We get subsequence convergence and global convergence. Now we can go even beyond that. That's a third paper, but that's still in the same paper. We can extend all this for free. I mean, I a bit exaggerate when I said for free, but let's say that it's more or less. So what do I mean? We can go to a non-Euclidean extension of that, and we are supposing here that the gradient of U is not anymore Lipschitz continuous. Okay. Then we can adopt the LSMAD, what is called the smooth adaptability, which is essentially asking the existence of a kernel H so that the difference of these two is a convex. This translates to an extended descent lemma. This also goes back to the work with Heinz, Boschke, Bolt, and myself. And then this is the usual Bregman distance. And then we can derive both the parallel and the alternating Bregman proximal scheme. We can build exactly the LSMAD property. It's actually neat because the Lipschitz constant is 1 in that case. You can see all the analysis in the paper, of course. This is a step of the U. For the V, that's exactly the same. We can do the analysis for both. Okay, so in time, you are aware this paper was just published online in Mass of War. You can go to my homepage for more. Thank you very much for your attention. And rarely I am finishing your talking time. I mean, but you
Thank you very much.
You pushed me.
Thank you very much.